Hello and welcome. So we'll be solving another question on bending stresses in a beam. And the question says that to calculate the maximum stress induced in a cast iron pipe of external diameter 40 mm of internal diameter 20 mm. It means the external diameter of the pipe is 40 and the internal diameter is 20 mm. All right, and the length 4 meter when the pipe is supported at its end. You understand? So if we have a concentric pipe, and if you cut it, you will see something in this form. I don't know in engineering. You cut, this is what you are going to see. All right. So, and don't forget, they are told that it is supported at both ends. So it is nothing but a simple supported pipe. That is just like a simple supported beam. All right. So, and it carries a point load of 80 Newton at its center. So the first thing you are going to do is to draw the pipe. This is how the pipe is going to look like. All right, you can see concentric, something concentric. So this is the circular, the external cycle and the internal cycle, and the diameter is 40 mm and the internal diameter is what, 20 mm. The length is 4 meter and is carrying a point load of 80 Newton. So the next thing you do is to bring out the given parameters. The external diameter is 40 mm, internal is 20 mm, the length is 4 meter, so which we are going to convert to what? Millimeter, multiplying that by what? 1000, you get 4000 mm, and the weight is what? 80 Newton. All right, so for us to start with this question, the first thing we are going to calculate is the maximum bending moment of this beam. And of course, I just mentioned that this beam is nothing but a simple supported beam. And if you follow our video in the application of flexural equation, you will know the formula for a simple supported beam that carries a point load. You can click on the link displaying on your screen. You are going to get access to the video. All right, so the formula for the maximum bending moment for a simple supported beam that carries a point load is nothing but maximum bending moment is nothing but WL divided by what? By 4. All right, so and the next thing we are going to do is just to substitute all these parameters for our load and length. So our load is 80 multiplied by our length, which is 4000. All right, so divided by 4. So if you do this, you are going to get the maximum bending moment to be equals to 8 times 10 to the power of 4. 8 times 10 to the power of 4. That is 80,000 Newton per what? Newton millimeter. All right, Newton millimeter. So the next thing we are going to consider is the what? Is the moment of inertia of this section. This is a hollow circular section. So for a hollow circular section, the moment of inertia is given to us as what? Pi all over what? 64 into what? Into the d to the power of 4 minus d to the power of 4. All right, so if you substitute here, you are going to have this to be what? Pi all over 64 into what? Into our d is 40. So we are going to have 40 to the power of 4 minus 20 to the power of 4. All right, so if you press this value in your calculator, you are going to have this to be equals to 117,809.7, and don't forget our unit is going to be mm to the power of 4. All right, the next thing we are going to calculate here is the is the distance from the neutral axis to the outermost part of this section. All right. If we section this, let's say this is the center of this cycle. So if we decide to section it either in this direction, all right. So of course, from our lecture on sectional modulus, I have explained this concept. You can either section in the x-axis or in the y-axis. But if you are considering your y value, that is, which is the distance between the neutral axis to the what topmost part of the section, it is always going to be what for a concentric section is going to be, we are going to consider the external part. Is that clear? All right. So now what will be the distance from this top section to this side? So of course it's going to be, since we know that the diameter is what 40, so the distance from this point to this point, or from this point to this point, will be equal, which is going to be what 40 divided by 2. So our y max will be equals to 40 divided by 2, which is going to be what 20 mm. All right, so that will be the value of our y max. All right, so now you are going to recall carefully from the flexural equation. From flexural equation, we said that maximum bending moment all over the moment of inertia will be equals to stress. That is the maximum stress divided by what? Y, and which is known as what? Y max. All right. So if you make your maximum stress the subject here, we are going to have our maximum stress will be equals to maximum bending moment multiplied by Y max divided by what? Divided by I. All right. So we are going to substitute for this. Going to substitute there. So we are going to have our maximum moment to be equals to, what is our maximum bending moment? Our maximum bending moment is 8 times 10 to the power of 4, then multiply by our y mass, which is 20, then all over what? All over I. Our I is 117,804.7. Okay, 9.7. all right. So the maximum stress will be equals to, so if you press this value correctly, you are going to have 13.58. So it's going to be 13.58 Newton per millimeter square. So here is going to be the solution to the above question. So I believe this question is well explained and well understood. You can let us know that in the comment section. Thank you. Stay tuned for more interesting video.